Earth 2.0, why it matters. Maybe I should start by asking what is Earth 2.0? According to NASA, Earth 2.0 is Kepler 452b, which is entitled Earth's Bigger Older Cousin. And they have some briefing materials that we'll go through briefly. NASA will host a news teleconference at noon EDT Thursday, July 23. Obviously, this is done before July 23, to announce new discoveries made by its planet hunting mission, the Kepler Space Telescope. The first exoplanet orbiting another star like our Sun was discovered in 1995. Exoplanets, especially small Earth-sized worlds, belonged within the realm of science fiction just 21 years ago. Today, and thousands of discoveries later, astronomers are on the cusp of finding something people have dreamed about for thousands of years: another Earth. The briefing participants are listed. John Jenkins, incidentally, wrote the paper that's given. And a replay of the teleconference is available until midnight CDT on August 23, so you still have time to look at it, and there's a toll-free number, and then there's a toll number if you want. The NASA Media Advisor, they have a link to that, and that NASA press release. We'll be looking at the press release in just a bit. The research paper that these findings are based on, as published by the Astronomical Journal of July 23, 2015. So they waited till the journal article was out. And the journal article is available, and we'll look at that as well. And I think that there's actually two links that they gave. And the rest of the press release was just basically a bunch of pictures with descriptions. You'll recognize our Earth with the sun behind it. December 2011, they discovered Kepler 20e, which is a very an Earth-sized planet, but it is so close to its sun that it's basically molten. Then Kepler 22b in December of 2011 is a very large planet, cool enough, but probably too large. And Kepler 1861, which is just nicely in what they call the habitable zone, but of a very small star, which means there's a couple of problems with it. One of them is it's subject to solar flares, and the other one is that it is probably tidally locked with the sun, which means that it always has the same face to the sun, which is makes living on a planet like that a little difficult. And then finally, Kepler 452b, which has an Earth day of 385, a year of 385 Earth days. And they have an artist's conception, which you will notice forms the background to the slide that I have. Then they have the Kepler system. This is at 182 in orbit around a very small star. You notice that it's about the distance of Mercury from its sun. Kepler 452 is actually a little bit further out than our Earth. And then of course this is for comparison the orbits of Mercury, Venus, Earth, and Mars. And you'll notice that our habitable zone extends out to Mars, although that's stretching it a bit. They have a number of Kepler small habitable zone planets, which includes one orbiting a sun-like star, that's 452. its star is slightly larger, and so therefore it's actually, even though it's further out, it's actually closer to the edge of the habitable zone. And again, the habitable zone is extended considerably beyond what I would consider a good extension, but whatever. And you can see there's a number of planets that are kind of in the habitable zone, most of them a little bit too hot, some of them in pretty good spacing. And that 186, that one around the dwarf, is actually out quite a ways from it, even though it's at the planet Mercury's orbit. Then they show how this is supposed to have changed during time, not so much because of the planet moving, as because with time, according to standard theory, the sun grows larger and hotter, and therefore the planet receives more light with time. You can see we're nicely in the middle of the habitable zone. Actually, as I said, I think this is a little exaggerated on the wide side, and Kepler 452b is starting to creep further on into there. Then they had comparisons of large stars, G stars, K stars, M stars of course being the smallest one, and here's our 186. And you can see there's a number of planets that line up there. Most of them being slightly larger than Earth, and if you're wondering why, it's very simple. In order to detect these, you either have to detect a transit or you have to detect movement of the sun in response to the planet. Well, it's a little hard to get a small planet like Earth to move a large sun. Kepler is about 5 times the weight of Earth, and therefore moves its sun just a little bit more. But that's not the whole story, and we'll come to that in a minute. And you can see they've discovered scads of other planets, most of which are very large, you know, in the Jupiter range or the Neptune range. There's a few of them down in the, or a number of them down in the Earth range, but of course this doesn't give you what kind of a sun they're going around. It's easier to detect the movement of a small star than a large star because it moves more. And the closer in the planet is to the star, the easier it is to detect too, because it's more likely to give you a transit. And then again, they've shown there's a number of other planets that are not confirmed yet, which may give you, we may wind up with Earth 3.0, 4.0, who knows. This slide I'm showing simply for completeness, but you will see that they're finding more and more of these planets as time goes on. And finally, here's the first one was found in Pegasus B, and it's a whopper of a planet, larger than Jupiter by quite a bit. And Kepler now is just a little bit larger than Earth. In terms of diameter, it's about 1.6 Earth radii. Well, we'll move on now to their announcement, and you get a better idea of what they're thinking about. NASA's Kepler mission discovers bigger, older cousin on Earth. And again, this is available on the internet. NASA's Kepler mission has confirmed the first near Earth-sized planet in the habitable zone around a sun-like star. This discovery and the introduction of 11 other new small habitable zone candidate planets marks another milestone in the journey of finding another Earth. The newly discovered Kepler 452b is the smallest planet to date discovered orbiting in the habitable zone, the area around a star where liquid water could pool on the surface of an orbiting planet of a G2 type star. They found them with smaller stars, but not with G2, like our sun. The confirmation of Kepler 452b brings the total number of confirmed planets to 1030. Quoting, on the 20th anniversary year of the discovery that proved other suns host planets, the Kepler Exoplanet Explorer has discovered a planet and star which most closely resembled the Earth and the Sun, said John Grunsfeld. This exciting result brings us one step closer to finding Earth 2.0. Kepler 452b is 60% larger in diameter than the Earth and is considered a super-Earth-sized planet. While its mass and composition are not yet determined, we don't really know, previous research suggests that planets the size of Kepler 452b have a good chance of being rocky. How good a chance? Well, we'll see. The first exoplanet orbiting another star like our Sun was discovered in 1995. Exoplanets, especially small Earth-sized worlds, belonged within the realm of science fiction just 21 years ago. Today, and thousands of discoveries later, astronomers are on the cusp of finding something people have dreamed about for thousands of years, another Earth. And to give you an idea of where this fits with the rest of our solar system, you can see Earth down here. 1.6 would be about here, and you can see that Neptune and Uranus are both quite a bit larger, and Jupiter and Saturn considerably larger, and of course the Sun, huge. That slide was from last week's presentation, also from NASA. While Kepler 452b is larger than Earth, its 385-day orbit is only 5% longer. The planet is 5% farther from its parent star, Kepler 452, than Earth is from the Sun. Kepler 452 is 6 billion years old, 1.5 billion years older than our Sun, and has the same temperature, and is 20% brighter and has a diameter of 10% larger. We can think of Kepler 452b as an older, bigger cousin to Earth, providing an opportunity to understand and reflect upon Earth's evolving environment, said John Jenkins, Kepler data analysis lead at NASA's Ames Research Center in Moffett Field, California. By the way, who wrote the paper that we're going to be looking at, or was the first author anyway. It's awe-inspiring to consider that this planet has spent 6 billion years in the habitable zone of its star, longer than Earth. That's substantial opportunity for life to arise, should all the necessary ingredients and conditions for life exist on this planet. If you just have water and organic compounds and wait a while, you'll get life, I guess. To help confirm the findings and better determine the properties of the Kepler 452 system, the team conducted ground-based observations at the University of Texas at Austin's McDonnell Observatory, the Fred Lawrence Whipple Observatory on Mount Hopkins, Arizona, and the W.M. Keck Observatory atop Mauna Kea in Hawaii. So basically they got some ground-based telescopes involved. These measurements were key for the researchers to confirm the planetary nature of 452b, to refine the size and brightness of its host star, and to better pin down the size of the planet and its orbit. The Kepler 452 system is located 1,400 light-years away in the constellation Cygnus. The research paper reporting this finding has been accepted for publication in the Astronomical Journal, and is also up, although I think they're still making final revisions before it's in print. In addition to confirming Kepler 452b, the Kepler team has increased the number of new exoplanet candidates by 521 from their analysis of observations conducted from May 2009 to May 2013, raising the number of planet candidates detected by the Kepler mission to 4,696. That's the basis for that one slide that had all the new planets on it. Candidates require follow-up observations and analysis to verify their actual planets. This one they're pretty sure is. And, I agree with them, as we will see. 12 of the new planet candidates have diameters between 1 to 2 times that of Earth and orbit in their star's habitable zone. Of these, 9 orbit stars that are similar to our Sun in size and temperature. and I'm going to skip over some of it. Jenkins, Giem et al. This is the paper on which all this stuff is based. And if you're curious as to what this plus is, that stands for Earth. And one with a dot in it will stand for the sun, as we'll see in a number of places. And that's the web address that you can look at it at. To read the abstract, we report on the discovery and validation of Kepler 452b, a transiting planet identified by a search through the 4 years of data collected by NASA's Kepler mission. This possibly rocky 163 plus 23 or minus 20, in the original those are lined up with each other, but I can't do that in this font. Radius of Earth planets, so it's 1.63 to be precise, although it could be 1.43, it could be 1.86. Orbits its G2 host star every 384.843, basically pretty precise days, the longest orbital period for a small transiting exoplanet to date. The likelihood that this planet has a rocky composition lies between 49% and 62%. Basically, it's a toss-up. The star's effective temperature of 5,757 plus or minus 85 Kelvin, and a log G of 4.32 plus or minus 0.09. At a mean orbital separation of 1.046, 1.03, 1.05, 1.06 probably. This small planet is well within the optimistic habitable zone of its star, recent Venus to early Mars. Optimistic habitable zone means we expand it to could it possibly, rather than a more conservative one that would include the Earth but not Mars or Venus. And slightly outside the conservative habitable zone. Okay, by now it's actually outside of the conservative habitable zone. Runaway greenhouse or maximum greenhouse, so it may be already toast by now. The star is slightly larger and older than the Sun, with a present radius of 1.11 sun radii. Could be actually about the size of the Sun, 1.02. And I think that those are actually one standard deviation, so it could be even smaller than the Sun. As we shall see, they originally thought it was. And an estimated age of 6 billion years. Thus, Kepler 452b has likely always been in the habitable zone and should remain there for another 3 billion years. Well, the optimistic habitable zone. I'm not going to read the whole paper, obviously. We don't have time, but I'm going to go through some interesting parts of it. The introduction to the study of exoplanets began in earnest just 20 years ago with the discovery of 51 Peg B, a hot Jupiter. That's that giant planet we saw earlier, with a 4.2-day period orbit of its host star. This discovery was followed by a trickle of hot Jupiters that became a torrent of giant planets over a large range of orbital periods, chiefly by means of radial velocity observations. Big planets make their suns move, and so they're easier to detect. Transit surveys were already underway as early as 1994. A transit survey means that you can see the sun darkening as the planet moves in front of it. Basically, it's partial to annular eclipse of the sun. But it's only a small part of the sun's that's blocked, so it's not anywhere near the total eclipse we see on Earth. And rapidly gained momentum once the hot Jupiter population was established. These surveys did not bear fruit until 2000 when the Doppler detected planet HD 209458b was seen in transit. So most of the time you don't see it. Well, why is that? It's very simple. Think about the Earth and the Sun. Imagine yourself out in Alpha Centauri or some other star way out away from the Earth. Their sun distance is 149 million kilometers, 93 million miles if you prefer. The sun's radius is 696,000 kilometers. And if you add to that, the Earth's radius is 6,371. That means that in a certain portion, the Earth will just barely clip the sun, and then further in, it will completely block part of the sun's output. And so the maximum of any blocking is going to be a strip that is the Earth's diameter plus the sun's diameter, because you've got on both sides, which is 1,405,000 kilometers. Now, if you take and divide the sun diameter by the Earth-Sun distance, it's equal to 1 in 106.45, or 0.009394. If you like, it's almost 1% of the arc. Because of that small distance, sine x equals virtually identical to tangent x, which equals identically x itself in radians. And if you take a strip and run it around of where the Earth would block the sun somewhere, and divide that by the entire sphere of observations that could be made, that area divided by the total is equal to the width divided by 2 times the radius, which is equal to 1/2 of this number, or about 1/2%. And what that means is there's a probability of about 1 in 200, 220, something like that. That if you pick a random star out there and they're looking at the Sun-Earth system, that the Earth would go in front of the Sun enough to where they could detect that there was a dimming of the Sun's brilliance. Most of the time you can't see it, which is why you haven't seen any more transits than what you would expect. And you're going to see that this particular one does in fact have a transit. Perhaps the most exalted goal, and one that remains tantalizingly close, is the discovery of a sufficient number of near-Earth-Sun analogs to inform estimates of the intrinsic frequency of Earth-sized planets in the habitable zone of Sun-like stars. So they really want to know, are there any Earths out there? That's what the whole point of this thing is. The habitable zone is an evolving concept, here taken to be that range of distances about a star permitting liquid water to pool on the surface of a small rocky planet. Well, small relatively. The Earth is a pretty big planet, but compared with Jupiter, for example, it's very small. So they're looking for planets that are about the right distance from the Sun to have water, and small enough that they've got rocks on which water can sit, instead of a gas giant that doesn't really have much of a surface. To skip on down a ways, discovery. Kepler 452b was discovered in a test run of the Kepler Science Operations Center 9.2 code base in 2014. They were using their computer to look for stars that dimmed regularly, and just kind of, it came up. In 2014, in May, when one of us inspected the Planet Search pipeline results to assess performance of an enhanced pipeline code base for small, cool planets. So they were kind of trying to set up and, oh, look what we found. According to the data validation pipeline module, the transit signature of this object featured 4 10.5-hour, 200 part per million deep transits. That's 1 part in 5,000 that the star dimmed. Not very much. Spaced 384.846 days apart, a radius of 1.1 radius of the Earth, and an equilibrium temperature of 221 K, assuming an albedo of 0.3 and full distribution of heat. Wait a minute. I thought it was 1.63. Equilibrium temperature of 221 K is pretty, that's a little cool, actually. 273 is freezing water, and 373 is boiling water. So we're talking few degrees below 0 centigrade. That's not what you heard, was it? This transit signature was not identified in the previous search through all 4 years of Kepler data within this SOC 9.1 code base conducted in 2013 August, most likely due to overly aggressive consistency checks put in place to reduce the large number of false alarms by instrumental effects. So when they were doing this originally, they just zipped right on past the data. Then when they went back carefully after a very careful computer search, they said, oh, looks like we have a few dips here of 200 parts per million. And then they went back and looked at it, and sure enough, they were all there. But they didn't see it at first. After all 4 years of Kepler data had been reprocessed with the deployed SOC 9.2 codebase, Kepler 452b's transit signature was re-identified in the recent run of the planet search pipeline in 2014, in November. So, this was not obvious from the data immediately. We expect that several more terrestrial planetary candidates will be identified when all the new SOC 9.2 TCEs are fully vetted. So they're looking for very small effects, and occasionally they're finding them, and this is one of them. This is the first planetary signature detected for this particular star, which is noteworthy given the long orbital period and the high fraction of multiple transiting planet systems identified by Kepler. If there are planets in orbits interior to that of Kepler 452b, either they are inclined so as not to present transits, or they are too small to detect against the photometric noise for this 13.4 magnitude star, which averaged about 40 parts per million at 10.5 hour timescales across the 4-year data set. So there's some natural scatter, and it could be covering up smaller planets. The stellar parameters for this star at the time of the test run included an effective temperature of 5,578 K, but a radius of only 0.79 of the radius of the Sun. Interesting. It's supposed to be smaller than the Sun instead of larger, as we heard earlier, yielding a planet with a correspondingly small radius of 1.1 times the radius of the Earth at a mean separation of just about 1 astronomical unit. That is just about the size of the Earth, 0.99, or the size of the Earth's orbit. The small stellar radius was due to an anomalously high log of 4.58, and I'm going to skip over some technical data and say that the word "other" is an interpretation or an interpolation that I'm making. Measurements indicated that the surface gravity of the star was overstated by the KIC, and thus implied that the planet is about 45% larger than it appeared in the data validation summary report produced in 2014 May test run of Kepler pipeline. Keep that in mind as we're looking at this. They thought the star was smaller. As it turns out, it's a bigger star, and therefore the planet's a little bigger than we thought. Kepler photometry, and then there's a bunch of stuff in there that I'll move over. But note that the individual transits are significant at the 4.75 sigma level, so that each can be credibly seen by eye in the long cadence data at 29.4 minute resolution. Now I'm going to give you a look at the data at first. And here's a transit, here's a transit, here's a transit, and here's a transit. And try as I might, I'm not able to see where there's a significant decrease in the data. That's probably because it's all jammed up and it's very hard to see all the data points. However, if you look at another plot, which is spread out a little bit more, here, this is the four of them superimposed on each other. You can see that there is a significant decrease in the data here as compared with this. But you can see how you could miss this. Remember, this is parts per million flux. And so you can see there's a considerable spread of the data here, but when you get to here, it drops down and then comes back up. Now, that is the data on which all of this other stuff is being reported. That and the spectrum of the star. And everything else is drawn from that. The data validation tests, discriminating events background, eclipsing binaries. They tried to eliminate the idea that one sun came in front of the other and obscured it. They did a statistical bootstrap test. They did a centroid analysis. They looked at contamination by other sources. And other sources include pulsating variables and eclipsing binaries that might have gotten light scattered from them. Pulsating variables are pulsating variable stars. And then to go on, they did spectroscopy. That's to try to find out how hot this star really is. And reconnaissance spectra, higher spectroscopy. So there's a whole bunch of stuff they did. And then they get to the host star properties. This is kind of trying to put this all together. Since this particular star is too faint for direct observation, such as interferometry or astroseismology, the derivation of stellar mass, radius, and density relies on matching atmospheric properties to interior models. What that means is they really can't see what looks like, what's going on. All they have is that data of how far it went down and how long. And so everything else is based on, but we think this star should be this big because it is this temperature and it has this much iron in it and so forth. And how do we know that? Because we have models of stars, and this is how stars should burn if they work according to our model. The properties of planet Kepler b, and then I'm going to go over one particular part. We also performed a fit forcing the orbit to be circular in our transit model. Forcing the orbit to be circular. They don't even know if the orbit's circular. And obtained thereby an estimate for the density of the star of rho, that's density, equals 1.1 plus or minus 0.3 grams per centimeter. Now that's basically the density of water. While this value is perfectly consistent with the spectroscopic work, it suggests that both the star and the planet may be somewhat smaller than indicated by spec match analysis. So maybe it's not as big as they think it is. And again, some other analyses that you can read if you want to. They're in the paper. Habitability and composition of Kepler 452b. Here we examine the probability that Kepler 452b orbits in the habitable zone of its star, considering the effects of unknown eccentricity on the habitability and estimate the likelihood that it is rocky. Of chief interest is whether the insolation flux, that's the amount of radiation that it's getting from the sun, experienced by Kepler 452b would permit water to exist in liquid form on its surface. Would it do that? Secondarily, we wish to examine the likelihood that it possesses a rocky surface upon which liquid water could pool. Could you have oceans, in other words? And to go through some of the other stuff, the effect of eccentricity on habitability. The eccentricity of the orbit of Kepler 452b is poorly constrained by the photometric measurements at best. They don't know. The difficulty with an eccentric orbit is that that the planet goes very close to the sun at one point and then goes out and then stays outside. So you could have most of your time either inside or outside of the habitable zone, even though the orbit has a period that, if it were circular, would be totally within the habitable zone. Well, we have a question here. Just a minute. We got the mic here.
I was just curious because if I'm reading my Bible correctly, verse in Genesis, it appears possibly that the earth already had water on it.
That's a possibility.
So we might not necessarily be looking at something that's inhabitable, but has
it
some
might not be habitable.
to,
It may have water all over the outside of it. That is true.
yeah.
Although that would be habitable, but only by sea creatures of various kinds.
Correct.
So we don't really know whether this thing is eccentric or not. To move on, composition, applying the MR relations of Weiss and Marcy, 2014, another model gave rocky probabilities of 40% and 64% respectively. Somewhere between 40 and 64%, 50%, maybe it's rocky, maybe it's not. And to move on, history of the habitability of Kepler 452b. This is talking about where it's been in the past. Given the similarities between the Sun and this particular star with respect to mass and effective temperature, and the fact that the orbital distance of Kepler 452b is essentially one astronomical unit, it is interesting to consider the habitability of this planet over the history of this planetary system. It is important to note that statements comparing the age of the star to that of the Sun are tentative, given that the estimated age for this star is heavily model dependent, and the 2 gigayear uncertainty estimated in Section 6 does not take into account variations of poorly constrained model physics such as convection and microscopic diffusion. So this is an estimate that you should take with probably several grains of salt. And to move on, conclusions, the identification of a 1.6 Earth radius planet in the habitable zone of a G2 star at a mean separation of 1.05 astronomical units represents the closest analog to the Earth-Sun system discovered in the Kepler data set to date with respect to the orbit and spectral type of the host star. Moreover, the small radius of this planet provides a reasonable chance between 49 and 62% that it is rocky, although in this case it is unlikely to have an iron core of significant mass. Why is that? Because if it had an iron core, it would be denser than 1.1. Earth's average density is about 2.5 or so. And to finish up, well, why is the Earth 2.0? Well, because it's like the Earth, and so it's the new improved Earth. Well, at least new Earth, I guess. What we know about Kepler 452, the most Earth-like planet ever discovered, is a not unusual title. This one is from The Independent in the United Kingdom, and you'll find titles like that in a number of different places. Earth 2.0 is kind of what it's been dubbed. Now, the question becomes, why does it matter? Well, Kepler 452b is a possible target of colonization. That's number one. If our Earth gets bad enough, can we ship off to another planet? Well, it'd be nice if it was a planet that wasn't too cold and wasn't too hot and perhaps had water on it. It could have life, which is what they really get excited about. That would mean that we're not alone in the universe, among other things. It would also, according to some people, and we're going to look at some of that, would mean that life could easily arrive by natural causes. Because, after all, it arrived here by natural causes, it arrived there by natural causes. So, well, of course, that assumes that it arrived here by natural causes, too. And there might be theological problems. Again, we'll look at some of that in just a minute. And in fact, there is an article called "What the Kepler 452b Discovery Means for Religion," and that one's on the internet, and there's the address. Since the recent discovery of Kepler 452b, more prosaically known as Earth 2.0, I thought that was the more fancy name, but whatever. Scientific and non-scientific communities have been abuzz with excited speculation. The existence of another Earth-like planet in the so-called Goldilocks zone, the circumstellar habitable zone around a star, with the right conditions to support liquid water, has reignited interest in that perennial question: are we alone in the universe? I'm going to skip a few other things, and it says, what's in it for God? Earth 2.0 has also posed questions that go to the heart of religion rather than science. For Jeff Schweitzer, former presidential advisor on science and technology to Bill Clinton, Earth 2.0 represents the worst possible news for God and all who believe in Him. Whenever we consider space and all of its possibilities, it's easy, of course, to be dazzled by the sheer numbers involved. Some estimates put the total number of stars in the observable universe at a septillion stars. That's 1 followed by 24 zeros. But for Schweitzer, the numbers are irrelevant. It doesn't require billions or even millions of other possibly habitable planets. There only needs to be one other to disprove religious myth. In other words, even if Kepler 452b were the only other habitable planet besides Earth, it would by itself be sufficient to discredit the idea of a God. Whoa. Not surprisingly, the announcement of its discovery is therefore pregnant with both scientific and theological significance. Well, but before we rush to abandon whatever faith some of us still have, it's worth considering the basis on which Schweitzer proclaims the death of God. Unfortunately, he knows next to nothing about textual exegesis, the critical examination of a text. His argument that Kepler 452b definitively disproves God rests on the thinnest of exegetical wafers. It goes like this. Schweitzer wants us to accept that because the Genesis creation narratives speak of life in the earthbound singular, any proof or even possibility of extraterrestrial life falsifies the Bible's own claims about the God who instructed its authors. If there were other lives or habitable planets apart from Earth, God would surely have told the biblical writers to mention them. Because he didn't, the Bible is therefore false and its God non-existent. Of course, at the most basic level, Schweitzer is right. The Bible does only concern itself with the creation of life on this planet. For all its talk about the heavens, there's no mention of other possible Earth-like worlds. I'm going to come back to that in a bit. Nor do any of the writers inquire into the existence of alien life forms. But is this really the fatal oversight that Schweitzer believes it to be? The rabbis were aware of, but largely uninterested in cosmology as such. Why? Because they were sufficiently concerned with the problems of this world without worrying about speculative possibilities of any others. That is to say that the Bible is simply uninterested in the maybes and what-ifs of astrophysical abstraction. On the contrary, the Bible in its entirety provides a narrative framework for understanding how this people, the community of Israel, and then later the Church of Jews and Gentiles, relates to this God. There is something deeply grounded about Scripture's intention Do not inquire abstractly into what may be, but to ask instead, how then should we live here and now with ourselves and with one another? To require of the Bible that it also engage in cosmological speculation is as nonsensical as demanding that we find a recipe for butterscotch duff in Newton's Arithmetica Universalis. I like that line. This is not, of course, to deny that the discovery of Earth 2.0 is freighted with theological significance. No longer living in the time of Scripture's composition, we do not have the luxury of ignoring the scientific realities that were at one time mere curiosities. Skipping a little bit, but what does it mean to say that God is pro nobis, or for us? Is he also for all other possible life forms? Why not, we might ask? Is there still something unique about life made in God's image that may not be necessarily true of any other life types? Can we in good faith confess that God is the maker of heaven and the earths? Perhaps, particularly, is there anything in the Scriptures that would prevent us from making such a confession? These are just some of the questions that we should carefully ask. But in all honesty, such questions are only in fact the natural extension of questions that have already been asked by the various eco-theologies. Eco-theology has intentionally sought to destabilize the anthropocentric, geocentric narrative of normative doctrine. To ask now about the impact of extraterrestrial habitation on our concepts of God is different only by degree and not by kind. But if we are to do so, we should be guided by a far more sophisticated exegetical grammar than that employed by Jeff Schweitzer. We will need to learn how to read our foundational religious texts with nuance, with an eye to the discursive whole, rather than contenting ourselves with facile proof texting. Theology, just as much as science, needs to keep an open mind and an open heart. If it does so, then that will be, in fact, good news for God. Obviously, Mark Lindsay is not as impressed as Jeff Schweitzer with the ability to kill theology with the discovery of life on other planets. And we must confess that we really don't know whether there's life on this planet even. A more balanced approach, I think, is found in the article Kepler 452b, 4 reasons to get excited about Earth 2.0, and 4 reasons you're still going to die on Earth 1.0. And he says, let's get excited. 1, it could be near identical to Earth, and he has a bunch of stuff behind that, which is an interesting reading. 2, it's in its own Goldilocks zone. 3, it has 1.5 billion years on us, so maybe it's got life. And 5, it stands a chance of having life on it. OMG. Let me calm you down a bit. 1, we have no way of getting there. And he follows that with 2, we don't know for sure if there's water. 3, even if there was water once, there might not be any more. Remember, this thing is approaching the inside of that habitable zone and may soon may have a runaway greenhouse effect, sort of like Venus has. And 4, we're a few years from knowing anything for sure. Getting, this is 100 light years away. It's going to be a long time before we get there. Now, my own take on it is the actual data are rather sparse. We know the spectral type of the star. We know that it dims periodically. And the rest of it is all extrapolation. Sometimes reasonable extrapolation, but extrapolation nevertheless. The projected world has a roughly 50% chance of not even being the right type of planet. It doesn't have really a surface for water to be on. Whether there is a runaway greenhouse effect is not clear. It may have one already. And finally, theology would not be disproved by life or intelligent life on this planet. You have to recall that in Job, it talks about the sons of God shouting for joy at the creation of our earth, which implies that there are sons of God out somewhere. Are they all in heaven? Maybe some of them are on different worlds. And of course, Ellen White's visions have other worlds populated. So I don't think that Adventists have a particular problem with that. I think Adventist theology specifically allows for life on other planets, perhaps in other solar systems. Finally, finding definitive evidence of life on Kepler 452b or any other planet would not prove that unguided natural causes could produce life. If intelligent design produced life here, presumably it could do so elsewhere. This is actually easier than believing that blind natural forces did it twice. But that's my opinion. Now it's your turn. Yes, comment here.
Several points. Number one, I find it fascinating that Schweitzer now contends that this would be the death knell of God. I thought that evolutionists had already settled this question before. How is it that this keeps being done over and over and over? One is led to conclude that obviously he wasn't killed well enough before. Is that not the case? I mean, what else could one possibly conclude? If on such, how should I say, flimsy, sparse evidence, one immediately jumps to these grand conclusions, one is led to believe that one is desperately looking for such tools to accomplish that feat.
That is
clearly meaning that one has not achieved it yet.
That is the natural conclusion, I think.
It seems. Okay, enough said about that. The other thing is, if the contention is in fact correct that there is no iron on that planet, that would imply a lack of a magnetic field.
It would.
If there is no magnetic field to protect the planets from sun's radiation, how stable would any life that would emerge possibly be? I mean, do you see the whole point?
One would have to deal with
we use radiation.
Solar radiation.
Yes, solar radiation. Even on this planet, we use radiation to sterilize a room.
And in this particular case, the Earth has a magnetic field that protects it from
that protects
solar
us
radiation.
from it. That's exactly correct. So, you know, this whole issue, just because there seems to be a blip someplace too far for us to, at this stage, conclude much, perhaps we should. This is very interesting, but I think it would be wise if we kept it at the very interesting and kept pursuing this interest rather than immediately jump to grand conclusions. And that brings me to the third point. Doesn't the book of Job say that the sons of God assembled before God, and Satan came also? What that presents before us is that there are assemblies before God of representatives of other civilizations elsewhere. They come
almost of other worlds, because
yes,
the devil
of
is
other
claiming
worlds.
this one.
That's what is implied. And of course, from our planet, the devil shows up, because none of us are traveling.
Yeah.
And
well, in fact,
see,
the way he approaches it, he says, God says, "Well, where'd you come from?" And he said, "From walking to and fro
up and down,
and up and down." And for our modern English minds, we miss the implication. That's what a king does in his domain.
That's what it is.
And he's saying, "I own the place."
That's it. So you see, the other representatives are there for the conference, yes? And basically Satan comes to steal the show, so to speak, with his grandiose claims. He was defeated then. What do you suppose is the chance that he is likely to win today? Yes, of course. Lucifer. You know. And let's say that there are intelligent beings on this planet. Let's say after all the dust settles, it's a beautiful planet and intelligent beings there. And we actually got there. Do we suppose we're going to teach them evolution, or might they have something to say back to us?
Actually, we were watching you, and it was pretty
We
nice
were wringing our hands and shaking our heads, wondering what's wrong with this planet.
There's two things I see here. One, God asked Satan, where are you coming from? He wouldn't ask where you're coming from if there were many places he could have come from. Another thing is when you talk about, and that's a good piece of humor, about death of God, it sort of makes one feel a little more confident in the resurrection, doesn't it?
How many times does he need to be killed?
Yeah.
Okay. Can we pass the mic up to Tim here? There we go.
Yeah, I just in listening to your presentation, one of the things that was on my mind is, and also listening to Danilo, how many papers or serious studies have been done that actually list out the number of absolutely necessary factors that a planet would require for life to simply exist on it.
Not sufficient, just necessary.
Yeah, just necessary. Because obviously sufficient is a whole nother ball of wax, but just simply necessary, because it seems to me that what they're calling a habitable zone actually doesn't come close to encompassing the necessary requirements of life, at least as we know it. Even with all of their jigging there too, which kind of was interesting to me. I mean, the idea that life would exist on a planet that's substantially cooler than 273 Kelvin seems rather optimistic, unless it has an incredibly hot core or something that might be heating from the inside out.
Well, I think they're revising their estimation of the temperature.
Okay.
I mean, it struck me that they started out with a small star, a small planet, and a very cold planet. And then as they started looking at the spectrum a little bit more, they said, well, maybe it's actually a larger star, which means a larger planet, and which means that the planet's getting more solar radiation, is probably hotter. And then afterwards they say, well, maybe it's not really quite that large. And, you know, it's all being done on this little tiny dip in, you know, you get the feeling that this is huge extrapolation.
Well, exactly. And that was another thing, and I didn't want to really go off on this tangent, but I imagine myself trying to publish a paper in my area based on that much evidence, and I don't see it being published. But anyway.
My question to you is if you have any information. There's a Project Lucifer, the Vatican's observatory in Arizona. Do they have any input on this? Do they have research? Do they have information on this? And the other thing is...
well, before you go to the second one,
Okay.
I'll just say to the first one, I'm not aware of the project.
Okay.
I didn't run across it in a very cursory Google search. You have to realize that they're, you know, probably 100,000 articles at least on that you can find if you're searching for these kinds of terms. So, you know, who knows what whether there isn't something out there published. And of course, if you're particularly conspiratorial, maybe it's not published. But, you know.
What about what relation does this present to the theory of the cosmological constant, mathematically, or?
Probably not much, because this particular planet is within our galaxy, and so it's not going to make that much difference in terms of how galaxies are supposed to be separating from each other. This is all our local area, and won't show any kind of cosmological constant.
Well, I think you missed the implications of what I'm saying about Genesis 1. Remember I said we don't know whether the world is all land or water, or whatever. And I had something I was going to say about this comment, but I forgot what it was now.
That's okay. We'll move on to another commenter.
Well, just a question, really. Do we necessarily have to confine God to have other worlds, other orbits, other universes like ours in order to create them? I mean, he could have all of those others in a completely different paradigm as far as temperature and orbit and all those kinds of things. That I would like to know if someone can tell me. I mean, this may be a totally stupid thought, but is it possible? I mean, we're looking for other planets to live on in case Earth gets too troubled. Why? Who says that that would even be the case, that all these other planets are like Earth enough for life?
Well, some of them clearly are not. Some of them, for example, in our own solar system, nobody really wants to live on Pluto.
Right.
Even though I suppose that at least for a while it's physically possible. And there are gas giants that are, way too close to their sun, at least according to the calculations that we make using standard cosmology, whose surface temperature is like 900 or centigrade or so, which is enough to melt a good share of rocks. And so those kind of planets are not going to be habitable. And so the answer is there are plenty of planets that are not habitable.
Well, like if you go to Yellowstone, and before they believe that life doesn't exist at such and such a degree of temperature, and yet in all of those thermal ponds, so to speak, they have found life existing where we thought it was impossible.
True, but there's a bit of difference between near the boiling point of water and especially near the boiling point of water at altitude, and getting something that's like 900 degrees centigrade is pretty hard to exist.
Mm-hmm. Well, you can tell I'm just a lay person, not a scientist, but I've wondered about that.
Yeah. We have a question here and then one there.
Yeah, I'm interested in the data and the reworking of data. And parenthetically, I'm deeply suspicious of the reworking of any data. But having said that, we see that there's been two sets of measurements, or sets of interpretation of data, which have changed the density of this planet to not a lot more than water, which basically excludes iron, as we've discussed, and therefore excludes probably the presence of a magnetic field, which is important. However, we have to remember that measurements of density are in inverse proportion to the cube of a radius. And therefore, very slight changes in radius make a big change in volume and therefore density. And we're talking about measurements that, you know, we've already gone from 1.1 to 1.6 or 0.99 to 1.6, which is a big difference. So it just points out that these, what we think are measurements, are based on what looks like one measurement, which you've already demonstrated is subject to a fair amount of speculation as to its accuracy. Just a comment.
I think we have to be really careful about our extrapolations. Now, I'm not saying this as a person who's threatened by the possibility of a civilization out there. I'd actually be pretty happy to have it there. I suspect that we won't get any news from it. For one thing, if you think about it, the very first broadcast that was big enough to get out of Earth's atmosphere in a significant way was probably a speech given by one Adolf Hitler. If I were an inhabitant of a world that was receiving that about now, I think I wouldn't want those people around.
Just one other comment too. I had an internet conversation with a group that were strong creationists and Christians. And that very point was brought up about the possibility of inhabitable worlds elsewhere, which is perfectly consistent with Adventist theology. And they absolutely reject that possibility. And I think that's common among evangelical Christians, that they will not accept the possibility that there are perfect other beings other than angels elsewhere. For some unknown reason, and I can't figure it out, they won't accept it.
That's one thing that it's possible that the parable of the 99 sheep was not just about a person, but it was also about an entire world.
Interesting that they had no evidence of iron, because in a carbon-based life form system, iron is essential for your hemoglobin oxygen transport. So that makes it very difficult for a carbon-based ecology. But there's some speculation that there could be a silicone-based ecology, according to certain researchers, which would be rather interesting if there are other individuals that God has created that have entirely different types of homeostasis in their systems based on other elements of our element, and we may not even know all of the different types of elements that are available to God. There may be other element tables that have entirely different type of nuclear structures that we have no way of even coming across, because we have no way of discovering them because they're not available to us.
Well, that's a possibility. I would take that with a little bit of a grain of salt, because there was a case of, and in fact we have a Sabbath school that's on the video archives, on arsenic-based life. And that turned out to be, well, let's just say unconfirmed.
Yeah, just in response to the silicon-based life idea, that has been examined, I think, and probably rejected by most people who are seriously wanting something like that. There are problems with the polymerization of silicon. That carbon is, the bottom line is, carbon is a very, 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 very special atom, and the idea of basing life on other atoms that we have studied out there is pretty optimistic.
The same way as oxygen is a very special atom.
Yeah.
I mean, you have basically oxidizing capacity that is able to be floated around in the air. Sulfur just won't do that.
Yeah. And nitrogen happens to be pretty special in and of itself too. I mean, you could go on down the line. There is a reason why life is the way that it is. And there were a couple of other things I had to say, but we'll just leave it at that.
Go ahead.
Well, that's what we think. I was saw something just recently about when they created the nuclear bomb, or the atom bomb, that they created a new element. I think it was plutonium, but some of you guys that have a science background might know. What that is.
Well, one nuclear bomb is based on plutonium, which is, I don't know if I'd say it's not naturally found, but it is found in such small amounts that it is completely trace. There's no way you're going to mine enough plutonium from the entire world to make one bomb.
Yeah.
I think the comment on silicon-based life has probably come about because silicone is flexible. And silicone, of course, is not just silicon or oxygen. It contains a lot of carbon. And that's maybe the way people speculate that, you know, there could be flexible structures like life based on silicon. But if you have a polymer of silicon and oxygen, you've got rock. It's just not, you know, and it doesn't react.
And a polymer of silicon itself doesn't do too well.
Oh no.
It's hard to get the kinds of structures that you can get out of carbon, out of silicon, and it's just not as satisfactory. Anyway, coming back next week, we'll have some more fun. But thank you for coming, and we hope to be able to bring you some other interesting areas where science touches religion in some way.